Great, so thanks for coming. So this is joint work with Barak, Hopkins, Kellner, Kothari, and Petechin. So there's a lot of background for these types of problems, so I thought I'd go quite slow in the beginning. So let me first introduce the planted clique problem, although many of you may have heard of it before. And then I'll give you a gentle introduction to just the parts of sum of squares that we need. But what I'm really excited about is to get to this new tool called pseudo-calibration, which I think is an interesting blend between Bayesian and computational perspectives going on for actually resolving one of these questions. So let me first start with the planted clique problem, which is a basic and fundamental problem in average case analysis. It was introduced independently by Jerem and Kucera. Actually, a variant of it arose in earlier work of Karp in the mid-70s. In any case, what the planted clique problem is it's a model for random graphs, which we generate random graphs in two steps. The first step is we generate a standard Erdős-Rényi random graph in which each edge occurs independently with probability a half. Now in step two, that's where we plant a clique. So out of these n vertices, we choose a random set of omega of them. These are these red vertices, and then we plant a clique on them, meaning that every time there's an edge already in the Erdős-Rényi random graph, we don't worry, but if the edge is missing, we add it. Now the catch is that you don't actually know where this clique was planted. So at the end of this model, you're given a random graph along with a promise that it really does contain a quite large clique. And the basic question is to try and find the planted clique. You can ask this information theoretically, and you can also ask it for efficient polynomial time algorithms. So the name of the game here is really how large does omega need to be for efficient algorithms? Because the larger omega gets, the easier and easier the problem is, because the planted clique stands out more and more. So this is a random graph model. In fact, what's known about it? So if you just care about information theoretically, what's possible when you run in quasi-polynomial time, there's actually brute force search, which just looks for, let's say, a 3 log n or something like that size clique. And it turns out that brute force search in this case can actually find planted cliques all the way down to roughly the information theoretic threshold, that as long as the clique you're planting is size at least c log n, where c is any constant larger than 2, this works. But really the question is, what can you do in polynomial time? And then there's actually a huge gap. So let me first tell you about a very naive approach, which there's something pretty trivial you can do in polynomial time, which is the nodes which belong to the planted clique should have slightly higher degree. So in fact, if the size of the planted clique is at least root n log n, then each of the nodes that participates in the planted clique, its expected degree is enough standard deviations away from the expected degree of all the other nodes that you can figure out which nodes belong to the planted clique just by scanning through your vertices and picking out the vertices with sufficiently high degree. So this is a very naive algorithm based on degree counting, but it's actually not that far off from the state of the art in terms of what's actually known. So it turns out that you can actually shave this extra root log factor using spectral techniques. So Alon, Krivolevich, and Sudakov gave a polynomial time algorithm that succeeds as long as omega, the size of your planted clique, is at least c times root n for some constant c. And I should mention that there's actually a hybrid approach that you can do a little bit of brute force search by brute forcing for a constant number of vertices and then conditioning on their neighborhood that allows you to actually prune this constant down to any small constant you want, but you pay a huge price in the polynomial in your running time for your algorithm. And in fact, Deshpande and Montanari in fairly recent work gave a nearly linear time algorithm that's able to find planted cliques whose size is root n over e. So this is actually the state of the art for what's known for this very simple average case model. In fact, planted clique in the interim has found a lot of applications because it's such a nice model. So planted clique and variants of it, things like cadenza subgraph, which are harder, well, they found all this laundry list of applications, things like discovering motifs in biological networks, where the goal is to try and find within a given graph a subgraph that actually would be extremely rare to occur in an Erdős-Rényi random graph. So in fact, planted clique is a particular type of discovering motifs, but also many other works assume that planted clique is hard, in the sense that they believe that there's no polynomial time algorithm for finding planted cliques of size n to the half minus epsilon. And once you believe that that problem is hard, then you can actually get implications for a lot of other problems that span many other fields. So for example, when you talk about computing the best Nash equilibrium for some notion of best social utility, then it turns out that predicated on the hardness of plainted clique, you get hardness of computing the best Nash equilibrium too. It also gives rise to hard problems in property testing, hard problems like sparse principal component analysis, which give you another example of a seeming gap between what we can do computationally versus what we can do information theoretically, and also things like figuring out the RIP constant in compressed sensing. In fact, there's another way that you can exploit plainted clique, which is there's an inherent information asymmetry, which is if I plant the clique, I know where the clique is, but if I give you the graph, it might be hard for you to deduce where that planted clique is. And you can use this type of information asymmetry coupled with some conditional hardness results to do things like construct public key encryption schemes for, in cryptography. And you can also use it even within mathematical finance to create derivatives that you've manipulated that no one can tell are actually lemons in disguise. So planted clique has a ton of applications. This is a little bit of its CV, but really the main focus of this talk is on, the question, is it actually hard to find n⁻⁴ minus epsilon size planted cliques? So it's a great assumption which leads to a lot of implications in its own right, but actually, as we'll see, there are facets of this question, even known families of algorithms which are very powerful that were not known to fail, that could have spectacularly broken these conjectures. But just taking a step back, one of the major issues in this type of direction is that the usual way that we prove lower bounds on computational hardness is based on worst case hardness. So assuming things like p not equal to np, which is a worst case assumption, then a lot of times you can translate that through some clever reductions into other implications, other problems that are hard in a worst case sense. But the trouble is that planted clique is an average case problem. That's what allows it to have so many different applications. And because of that, there are actually complexity theoretic obstructions to hoping that the hardness of an average case problem can be predicated on worst case hardness. So this means that the bread and butter of one of the fields within theory, hardness of approximation, things like that, are based on reductions, and that's actually not useful for these types of problems. So instead we're going to give a different type of evidence, which is through really powerful families of algorithms, which I'll tell you a bit more about. That's where sum of squares comes in. So I'm going to try and give you a gentle introduction to sum of squares, because sum of squares is a fairly complex algorithm to wrap your head around. There's a huge literature on it. But let me try and compile and tell you the minimum you need to know about this. So the sum of squares hierarchy, I think the easiest way to think about it is through something called pseudo-expectation. So sum of squares actually started in earlier work of Shor and Nesterov, but it really took its modern form in work of Perillo and Lasserre. It's a very, very powerful family of hierarchy of SDPs. I'll tell you more about that later. But the way to think about sum of squares is actually to think about it in a slightly different way than through its proof system. The goal of sum of squares is to find some operator. This operator is E tilde throughout this talk, and it's called the pseudo-expectation operator. What this operator does is it maps any polynomial given to it of degree at most d in n variables to some real value. So you're looking for an operator E tilde called the pseudo-expectation, and the goal is for this operator to behave in a technical sense like it's the expectation over a distribution on solutions. In this case, a distribution on large planted cliques in a graph which we're given. So I'll formalize that later, but this is the intuition behind it. And then I'll show you what are the constraints that we need on E tilde so that it really does behave like it is an expectation. So there are some constraints on this operator, the pseudo-expectation, that are general, that they apply every time you want to use the sum of squares algorithm. So first of all, you want that E tilde is a linear operator on the space of these degree at most d polynomials. After all, the expectation operator would be, so we throw in that constraint. We want that what it does to the polynomial all1 is it maps it to 1. So it maps 1 to 1. The expectation does that too. Now this is what the real workhorse is of sum of squares, is in this constraint, that every time you give me a polynomial p and you take its square, the pseudo-expectation of the square of that polynomial should always be non-negative. This is definitely true if E tilde really were an expectation operator, and this is the workhorse behind what makes sum of squares so powerful. I should mention that all of these constraints I'm going to tell you, they have some caveats on how large the degree is. After all, the pseudo-expectation is only defined up to degree d polynomials. So in order for this to even make sense as an inequality, you need that the degree of p is at most d over 2. So for every polynomial of degree at most d over 2, this constraint better hold. So it's really important that the pseudo-expectation can't always be extended to even higher and higher degrees, because that's actually what makes it different than an expectation operator. Now there are some constraints that are actually particular to the plainted clique problem. So one thing to think about is that these x sub i's, you'd want them to behave like they're the indicator vectors of which vertices participate in the clique. So these x sub I variables are supposed to be 0, 1 variables themselves. And then if you take any 0, 1 variable and square it, you get the same thing as before. So this constraint just says that we're looking for Boolean solutions, that every time you give me a polynomial, actually whose degree is at most d minus 2, that you better have this self-consistency in how the pseudo-expectation operator behaves. Now let's start actually getting into what's plainted clique. Well, we're looking for large cliques, so we want that if these really behaved like indicator vectors for a clique, then we want at least omega of them to be on, because we're looking for large plainted cliques. So this constraint, you should really interpret it as being a clique size constraint. And the last and final constraint, this is the most important, is you better be giving me a clique to begin with. So if you think about, again, these x sub I variables as being indicator variables for a clique, then whenever we don't have the edge ij, we know that both of these can't be on, perhaps neither of them are on, because if they were, it wouldn't have been a clique. So this constraint just tells us that every time we apply the pseudo-expectation operator to a polynomial, times xi times xj, where ij is not an edge, we better get the value 0 because the pseudo-expectation is looking for a clique. So this is the mouthful of constraints. This is the most technical part in the talk, is wrapping your head around these types of constraints. But let me try and digest this a little bit for you. So we have the general constraints on the pseudo-expectation, and we have those that are specific to the plainted clique problem. Now the way to think about this is exactly as I was alluding to, that what would be a good pseudo-expectation operator is, imagine if ai through an really is the indicator vector of some omega-sized clique in a graph. Well, then we actually could easily define a good pseudo-expectation, which meets all of these constraints. Given some polynomial in these variables, all we would do is we would plug in whatever the indicator variables are for it, and lo and behold, that actually would meet all of these conditions. You know, one way to think about it is, why does it meet condition 5? It's just because if you give me this polynomial and I plug in this indicator vector, I am going to get omega because it's an omega-sized clique. This constraint holds because it is a clique, and it's easy to check each of these different conditions. Now this is great, but you know, the important thing is that pseudo-expectations are not just distributions on solutions. After all, I'm not trying to say that we can solve the clique problem in general. They can actually be quite different than actual distributions. That's why this word pseudo is so key in this talk. Everything I say should be couched with the word pseudo, because these aren't actually distributions. But in fact, the important thing is that there is an efficient algorithm for any constant d to find an operator, the pseudo-expectation operator, that meets these conditions if it exists. So if there really is a plainted clique, we know that there would be a pseudo-expectation operator, which would be the evaluation map. But in general, you give me a graph, you give me a bunch of these constraints, and in end of the d time, I can find some e tilde operator that behaves like it. The workhorse behind it is that constraint 3 really amounts to checking positive semi-definiteness of some end of the d by end of the d matrix, and that's really what's going on. But this is called the level d sum of squares algorithm. As you increase d, you get a more and more powerful family of algorithms that for any constant d still runs in polynomial time. And actually, this algorithm is incredibly powerful. So let me tell you a little bit about its CV. Yep?
So at what degree is the converse true? At what degree is a pseudo-clique?
N.
So not, omega
Exactly.
is not sufficient.
Exactly. Yeah. So at n, you are actually getting a distribution. But the issue is that you actually are getting strictly more power as you increase d, because you're getting higher and higher levels of consistency checks. Now, you know, SOS is a huge field, so let me just tell you a bit about its CV, right? So there are many other hierarchies of algorithms. There are things like Sherley-Adams, Lavash-Shriver, LS+. It strengthens all of them, for what that's worth. But what's actually amazing is the fact that actually there are problems like the unique games conjecture, which we knew integrality gap instances, which were very strong for all of these weaker hierarchies. And it was kind of amazing that actually SOS knows how to solve all of those instances in polynomial time. So for things like the unique games conjecture, which won the Nevelina Prize for, it's actually a conjecture that would have terrific implications for hardness of approximation. It's not even known whether the sum of squares algorithm breaks Cott's unique games conjecture. We know of no instances that actually fool SOS. So in fact, showing lower bounds for this algorithm is actually something which even for well-studied conjectures, we don't know, whether SOS believes it or not. It's also very successful as a convex relaxation for various problems like sparsest cut unique games. There's also this beautiful work of Lee, Raghavendra, and Stoyer that show that among certain types of problems, certain types of random CSPs, that it turns out to be optimal in terms of its size among all poly-sized LPs. So I'll just mention that briefly. It's also one of the best known algorithms for a lot of average case problems like planted sparse vector, dictionary learning, noisy tensor completion, tensor PCA. Now what this talk is really about is what happens when such a powerful algorithm is actually faced off with planted clique. So in fact, what was,
Can I ask another question? So far it sounds like an algorithm for proving something doesn't exist.
Certifying, yeah.
So what does it mean to say it is an algorithm for tensor PCA or dictionary learning?
So it's an algorithm that can be leveraged, these types of families of STP constraints to give you algorithms for noisy tensor completion. So there are these issues between translating between the certification problem, let's say for planted clique, certifying that a random graph GN 1/2 actually doesn't have a large clique versus the problem of actually finding it. As far as, we don't actually know a difference between these problems, but what we're going to show a lower bound for is actually the certification problem, which I'll get into what the relationship is between those maybe later. So in any case, the main question of this talk is, believe it or not, the following question is open. For this very concrete family of algorithms defined by pseudo-expectation, actually this conjecture about planted clique could have been spectacularly false. It could have been the case that actually there are polynomial time algorithms for finding not just n to the half minus epsilon, but n to the epsilon sized planted cliques. So what happens when you pit SOS against planted clique?
Uncle, quick question.
Yep.
Can SOS do something discontinuous like thresholding? I take a input matrix, threshold all the entries and do something.
No. So it has to, yeah, exactly. So a lot of those things, those algorithms, sometimes it runs in quasi-polynomial time because it takes a high degree of a polynomial as a surrogate for taking the infinity norm or something like that.
Very high degree.
Yeah, exactly. All right, so let me tell you our results. So we show a nearly optimal lower bound against SOS. And what's cool about this is it kind of comes from taking a computational Bayesian perspective, whatever that means. I'll digest that for you later. What we show is that the integrality gap of the level D sum of squares hierarchy is at least n to the half minus root d over log n. So to parse what the statement means is that whenever you plug in d equals little o of log n, so instead of just d is constant, d is 100, where you still get an ungodly high polynomial time algorithm, even if you take it to be a very large super constant, you're still not able to find better than roughly root n size planted cliques.
So, sorry, this is for one particular formulation of the regular formulation.
The regular formulation.
Okay.
Yep. So this actually improves upon a line of work that was started off by Mecca, Peteshin, and Vigerson. We built very heavily on these papers. It's later improved by Deshpande, Montanari, and then Hopkins et al. So what I'll do before I really get into what pseudo-calibration is, I want to tell you about some of the key insights from these papers and how that actually leads to the notion of pseudo-calibration. So in fact, aside from the results, what I really want to tell you is this new approach, which is called pseudo-calibration, which is I think yields a lot of insights into what makes SOS so powerful and how we can fool it. In fact, what's cool about it is whenever you take an average case problem, SOS is a very strong family of algorithms, pseudo-calibration actually gives you a recipe for constructing some way to try and fool it. And in fact, one of the exciting things is what we believe is that when this recipe fails, there's some intuition that actually that means SOS has lurking within it some interesting new polynomial time algorithm for other problems waiting to be discovered. So I'll just mention that as a little bit of philosophy. Now let me roll up my sleeves and let's be concrete about some of these things. So let me tell you a little bit about some of the previous work and some of the insights into where those things break down. What I first want to tell you about is something called the Mecha-Petechian-Wigderson moments. So really the question, just to refocus, is we're trying to understand, can we fool SOS into thinking there's a very large planted clique even in a graph like GN1/2? So what this means is, for even, if I was given a graph which really did have a planted clique, I could fool you into thinking there's a planted clique even on just the random part too. So this is one of the issues with trying to use SOS then to try and find it. But let's focus on this question. Is you're given a graph from GN1/2. It only has size log n cliques, but how can I create a pseudo-expectation operator that is wildly different than an expectation, but still meets all of these self-consistency constraints of the pseudo-expectation? So the usual approach is actually to take these weaker hierarchies and to actually adapt the integrality gaps in some way to stronger hierarchies. The amazing thing is that this actually works for a lot of random CSP problems like Grigoriev and Schoenebeck's work. But something actually goes wrong with planted clique, which we'll dig into. So the best things that are known about weaker hierarchies, so Feige and Krautgamer showed a nearly optimal lower bound, that they showed that the level D LS plus hierarchy, that again can be solved in n to the O of D time, that gets fooled into thinking that there's a root n over 2 to the D size clique in an Erdos-Renyi random graph. And if you take their approach and try and translate it into pseudo-moments, well, you have to do quite a bit more work, but what Mecha, and Wigderson showed was actually that the level D SOS hierarchy actually has integrality gap at least n to the 1 over D. Now this is quite interesting because, actually, if D gets larger and larger, you might actually think that maybe there's some hope that SOS really can find tiny planted cliques. Let me tell you about what their pseudo-expectation operator is. So what they do is the following. Well, the pseudo-expectation operator is linear. Let's first consider it just on monomials. So I'll use this notation x sub a to denote the product over xi of all I in a. And what the MPW moments do, is you can ignore this constant, it's not really important, is if a is a clique, they set it to omega over n to the size of a. So the intuition behind this is that, let's say the size of a is d. So you're looking at all size d cliques in a random graph, and they're roughly a constant times n to the d of them. So what you're doing is you're trying to hide as much information as possible and treating it like the actual distribution on solutions should be roughly uniform over those size d cliques. Now what you can do then is you can extend it by linearity to all polynomials whose degree is at most d, and this is what their approach was. And eventually what they do is, with this pseudo-expectation operator in mind, what they need to do is actually show that it meets all of those constraints. And their main technical tool are certain types of spectral bounds on very dependent random matrices. Not going to get into that either. But subsequently, Deshpande and Montanari improved their analysis, and actually for d equals 4, were able to show an n to the 1/3 lower bound. And Hopkins, Kothari, and Petechian, for any d, showed this type of lower bound. And you can check that actually for d equals 4, it recovers Deshpande Montanari as a special case. Great. But, these bounds are actually tight in the sense that these bounds really don't work beyond this size for omega. That's actually one of the main things that I want to emphasize is what goes wrong, because that's what's going to lead us to pseudo-calibration and to a type of computational Bayesian perspective. So this is, one of the main technical parts I want to get across is what goes wrong with those moments. So here's an abstraction of what's going on. Is, what I'm alluding to is the fact that these MPW moments do not work beyond this threshold. But the idea is actually to construct a polynomial that actually tells you something fishy is really going on with the way these MPW moments are set. So the key is that this polynomial is actually itself going to have coefficients that are random variables depending on the actual graph that you're given. So if you're given some Erdos-Renyi random graph, I'm going to use the notation Gij to denote the +1 variable if it's an edge and the -1 otherwise. And what we're going to do is we're going to consider the following explicit random polynomial. So given some graph G and given some index I where I is a vertex, what we're going to do is we're just going to sum over all j not equal to I of gij xj, all raised to the Lth power. So this is a polynomial, but let's see what happens, right? So if we were given this polynomial and we care about its expectation when we were actually given a sample with a large planted clique, what I claim is that this expectation is actually quite large. The way to think about this is there's an omega over n chance, roughly, that the ith vertex is in the clique. And if it's in the planted clique, then all of these other neighbors of it are all 1s and everything else is 0. And all of those edges correspond to plus 1s. So what we get at the end of the day is we get an omega in here raised to the Lth power and then squared again. So we get omega over n times omega to the 2L. But something fishy is going on, which is that when G is actually sampled from Gn1/2, the distribution that we want to fool SOS into thinking behaves like this one, then what actually happens is we take the expectation of the MPW moments over a random graph G. What we're really doing is we're taking this polynomial and we're squaring it. But the issue is that each of these variables, Gij, is itself independent. So the only way that we get contributions whose expectation is non-zero is if we actually mate variables so that this Gij variable occurs twice when we expand it out. So even though it looks like we have n to the 2L choices because we have a degree 2L polynomial, you really only have n to the L choices. You get n to the L times, well, these variables are trying to behave like omega over n, these x sub i's, because you want to convince someone that each vertex has roughly the same chance of being in a planted clique. So you get an omega over n to the L. Now the trouble is that these two things are different, so already you can see that something fishy is going on, which is that when m is actually too large, when it's close to root n, then actually this quantity is way too small compared to what it should behave like on the actual distribution. We want to fool you into thinking it comes from. So in fact, what this can do is you can massage this into an actual violation of those pseudo moments. That you can actually use that example to construct an explicit polynomial whose pseudo expectation really is negative, so SOS wouldn't actually be fooled beyond this. And the intuition behind this, which is now we finally get to the notion of pseudo-calibration, is that we were trying to be too aggressive, actually. So a good pseudo expectation is trying to behave like an expectation, and it's trying to hide information about what vertices actually participate in the planted clique, and it's trying to do so to convince you that you've learned nothing about which vertices do and which vertices don't. But you do learn something when you see a random graph, which is some nodes, just by chance, will have a standard deviation more degree than others. And what you should really be doing is you should think that those vertices are actually a constant factor higher probability of actually having been in the planted clique. So this is a type of constraint, a type of probabilistic deduction that sum of squares can make that the other weaker hierarchies cannot, and you really do need to take this into account to have any hope of fooling it. So, just taking a step back, there's actually a fix that you can do for d equals 4, so Hopkins et al. And independently Raghavendra and Shrem actually took this example of polynomials that breaks and explicitly added a correction term for it. These are the only polynomials that go wrong, and then you can show an n to the half minus little o of 1 integrality gap. And the idea is to add these correction terms for these polynomials to explicitly make their expectation over their pseudo expectation be what it should have been in the planted graph distribution to begin with. But one of the troubles is asking whether you can extend this to higher degrees. So even for d equals 6, the issue is that you can look at what all goes wrong. What types of polynomials have negative pseudo expectation of their square. And the trouble is that you need fixes for each of those. But each of those fixes then have their own random matrix-like terms that cause some other deviations. Those actually have to be fixed too. So the fixes need fixes, which need fixes, which need fixes. I think it goes out at least 3 levels. But the real trouble is that, extrapolating, it's not so clear whether you can actually carry this out. That, each of these fixes is very subtle with how to actually pick the right constants in front of it. So we're going to find a way to actually tune these corrections based on pseudo-calibration. So let me introduce pseudo-calibration. So what went wrong with the MPW moments was really this. that there was a simple function, which was Kellner's polynomial, which these two quantities behave differently. The expectation of the pseudo-expectation was different than the expectation under the planted distribution. So that was some type of Bayesian reasoning that SOS was able to take advantage of to refute those moments. But maybe we can try and make this equality hold for all simple functions. In fact, for all polynomials f that are low degree in both the Gij variables and the xi's, of which Kellner's polynomial is a special case. So the interesting thing is that actually once you have this definition in mind, everything becomes very formulaic, although technical. So if we're thinking about the pseudo-expectation operator, let's focus on just one monomial. We take xa, and with this monomial fixed, then what the pseudo-expectation operator is itself depends on what the graph is that you're given, right? For example, if the graph has a not being a clique, you better map it to 0. But in general, it could be some other function of when it is a clique. You need to figure out how to take the graph and map this particular pseudo-expectation to a real value. And let me define the Fourier characters. So in fact, we can take a graph T, and we can look at the product over all edges that belong to T of this Gij. Now what this tells us is that because the pseudo-expectation of this monomial is itself a function from the graphs to a real value, we can write any such function in terms of its Fourier expansion. That's immediate, right? So we know that whatever this function is, it has the property that it's some sum over graphs of some constant, the Fourier coefficient of t, times this character, chi t of g. And the real question is now not, how should we construct the pseudo-expectation, but how should we choose the Fourier coefficients? And the interesting thing is that once we choose pseudo-calibration as our desiderata, then the Fourier coefficients are completely determined for us. So we can use this expression for, this Fourier decomposition for the pseudo-expectation, and we can just plug in one particular simple function, which is a low-degree polynomial of the x's and a low-degree polynomial of the Gij variables, and we can write it out. So by linearity, we can pull out this chi t of g, because the pseudo-expectation is linear, so this is just a constant that depends on the graph. And then lo and behold, we can actually use this expression immediately and pull the expectation inside. But the key is that when we're working over Erdos-Rényi random graphs, then these different characters are actually orthogonal to each other under this measure. So what this means is that this quantity right here is 1 if t equals t prime, and it's 0 otherwise. So at the end of the day, what this tells us is that this quantity is true, that this expectation of the pseudo-expectation is exactly the Fourier coefficient, but now we can leverage pseudo-calibration, because pseudo-calibration tells us we want this to be equal to the expectation of this quantity, but over the planted distribution. So now everything is prescribed for us because we can compute whatever this term is. It turns out to be this expression. It's just omega over n raised to the size of the union of the vertices in T, which is a graph, union A. So everything is completely prescribed for us.
In the XA is taken, in the right-hand side is taken to be the indicator on the clique, right? On the planted clique.
Yes, yeah, exactly. So all I'm saying is once you have pseudo-calibration, you compute this from the Fourier expression, and you want it to be equal to this, and you can compute exactly what this is. This is what this quantity works out to be. It's a pretty elementary calculation. But now that's great, because what this means is that actually once we choose pseudo-calibration, our recipe is already fixed. We know what these Fourier coefficients have to be, which tells us what the pseudo-moments need to be themselves. Now there's a minor issue, which is we need to truncate. So I'll tell you a little bit more about that, but pseudo-calibration is the main thing I want to get across. So the actual pseudo-moments we use are we cut off at some threshold tau based on the size of Vt union A. So now I'm just going to tell you the skeleton of how the rest of the proof goes. So what we can show, what's not too hard to show, is with this notion of pseudo-moments, with this explicit definition, it follows by elementary concentration bounds, things like hypercontractivity, that if you look at how much E tilde of 1 deviates from 1, you can bound it based on whatever the threshold tau is. This is actually the reason why we need to truncate, is because if we went out to extremely high degree terms corresponding to bigger and bigger graphs T, then those high degree terms would deviate way too much to be able to control. But if you actually choose tau to be about log n, then what you can do is you can make this deviation be extremely small, enough so that you can actually correct it and make it be exactly equal to 1. And the same types of deviations allow you to show that things like the sum of xi is also very close to omega to actually fool another SOS constraint. You know, the rest of the skeleton is actually, this is kind of neat, is once you have this definition, things just kind of fall out for free. So one thing which was really the meat of the constraints is we better have that, you know, if A is not a clique in the graph, then we want the pseudo expectation of xa to be 0. That's a hugely important constraint in planted clique because we're looking for a clique. You don't actually see that occurring anywhere in this definition, but it turns out that this constraint actually follows from just the Fourier expansion of the and grouping together different terms. It's actually the reason why we chose this strange way of truncating instead of just looking at the number of vertices of T. We union it with A. And the other thing that one can prove is that it actually is pseudo-calibrated. So I'm going to omit all of these proofs, obviously, since I've got about 7 minutes left. But I'll tell you just a little more piece about what the main technical thing is. Once you have this recipe, those lemmas are pretty easy to prove. But actually, there's a huge elephant in the room, which is the really hard thing in all of these lower bounds is actually proving positivity. That for all polynomials p, the pseudo expectation of p squared is non-negative. So this step is always the most challenging in SOS lower bounds, as usual. And what this really boils down to is proving that a particular matrix is PSD. This is what the matrix is. And this matrix is the same type of matrix that arises in the SOS algorithm, that proving this positivity really amounts to checking a PSD-ness condition of a huge matrix. This matrix is indexed by size d subsets of I and j. But there's a huge issue that actually arises. This is the bulk of the technical work in the paper, is actually proving that M is PSD. The goal is to actually write M approximately as some PSD factorization, where if you think about this set T, that's a graph, and it's a graph that connects I and j because that's the set that indexes the rows and the set that indexes the columns. So what you really want is to write it as some sort of factorization this way, where k represents the size of some sort of minimum separator between I and j. That's the underlying graph theory. So we can think about one such graph. Imagine this were T, although I'm going to call it R, and it connects this I to this j. The idea is to actually look for the leftmost and rightmost separators. That gives us a way of decomposing the graph, and then what happens is that this is the thing that's supposed to be LK, this is the thing that's supposed to be QK, this is supposed to be LK transpose, and that's where the symbolic factorization comes from, is to try and write it this way. There's a huge issue, which is that in this decomposition, you're assuming that whatever graph you get out of this piece is disjoint from this graph and is disjoint from this graph, except at the boundary vertices. So what really happens is when you have overlaps between it, those are huge error terms in the approximate factorization that you need to handle. And the idea is to keep cutting away the graph. So instead you look for separators that separate I from the repeated vertices and from j, and similarly. And that gives you a new term in your decomposition, that it turns out that you can charge these error terms against everything else that's going on in the decomposition. So there are a number of problems with this, but I won't get into that. Let me actually, recap and actually step back and take a summary of this. So what I hope you got out of this talk is, first of all, we proved nearly optimal lower bounds against SOS for the planted clique problem, despite the fact that this assumption that you can't beat n to the half, you can't get n to the half minus epsilon in polynomial time, was a widely used assumption. It was actually not known that these very concrete, powerful algorithms like SOS don't already break that assumption, much the same way it's not known that they don't already break things like the unique games conjecture. What we give is we give a tool which we call pseudo-calibration, which is, when you're trying to fool SOS into thinking one distribution behaves like another distribution, there are all of these soft constraints, like when you have a high degree vertex, you should update what your posterior is on the chance you think it belongs to the clique. Now the issue is that there are no real distributions, these are pseudo distributions. So we introduce pseudo-calibration as a way to handle all of these low degree functions, but it gives you an immediate recipe for constructing how you should try and fool SOS. And what I think as an algorithms person is exciting is that maybe when this recipe fails, it means that SOS really is powerful. It's already been powerful in a lot of different settings, but it gives you at least an easier way to check whether you should be optimistic for your problem. And let me say something purely speculative and conjectural, because you should say at least one such thing in a talk. So I wonder, taking a step back, we're talking about an average case problem like planted Clique. And the main issue is that, how do we actually have evidence that this problem is hard? We can't rely on worst case assumptions like P versus NP, but we can prove lower bounds against very powerful families of hierarchies. I'll call that SOS evidence. There are other types of evidence for average case problems being hard, things like community detection with many communities. So are there any connections between SOS evidence and BP evidence, or what happens when they disagree? All right, so I'll end there. So thanks, and any questions you guys have would be great.
We have plenty of time for questions, in fact.
Since you ask for any questions.
Any questions?
Yeah. So when you go to the dth level of the hierarchy, you basically have to spend like n power over d running.
Yes.
Are there any strong evidence that this is the right running time, or can it be like 2 to the d or n square root of d?
In some special cases, one actually can do it in 2 to the d time, but those are very particular. So actually, Prasad and David know a lot about this, about speeding up these types of things. But in general, as far as we know, it does seem, not for particular problems, but in general, it seems that one requires n to the d, just because you have to write down that darn matrix to begin with. So if you talk about that, that positivity constraint, that e tilde of p squared is always non-negative, well, that's ranging over all p's, which are degree at most d over 2, which then the natural way to interpret that is as an n to the d over 2 by n to the d over 2 matrix, which then you want to be PSD. So, at the very least, in a lot of problems, you do have to write that down, although in some cases you can actually circumvent that issue and solve SOS much faster.
But you didn't try to relate it to ETH, for example, situation.
So can it be, let's see. Yeah, that's a good question. I'm not sure. I'll have to take that offline, but thanks.
So the question. So you have n to the 1/2 minus little o of square root of what? Log n over
D over log n.
d over log n. Okay.
Log n over d would be great.
But yeah. So question is, so do you think this is the correct order, or so this beats the lower Scriver, or you get the same behavior of
I want to say it beats it just because I want to be optimistic. So let's say it beats it without any evidence, but I'm really not sure about that.
I'm curious, the very last sentence you said about SOS perhaps being different from the thresholds. Can you think of some examples where this could happen?
So I'm not sure. So what I meant by this, and I would love to know the answer to this, is just, if one took cavity methods and replica symmetry breaking as evidence for hardness of average case problems, I wonder if there's any connection between pseudo-calibration and that, although that's a purely speculative thing. So I wonder if there's any commonality in what constitutes evidence, but I don't know. Purely conjectural.
So you mentioned that you said that the main problem with the previous constructions was inhomogeneity in the degree of the vertices. Mm-hmm. If you focused on random regular graphs, although that's tricky to obtain up around density 1/2, I guess you would still have inhomogeneity in things like the number of triangles.
Exactly.
And,
exactly. So there, that would just be richer. Exactly.
Sparse case regularity.
Exactly.
Kind of,
Once you have something that actually, once you have a subgraph count that really should change some notion of a computational posterior, whatever that means, then it does seem like SOS takes into account that type of reasoning. So one thing that you can say is you could optimistically hope that, this type of self-consistency in the pseudo-expectation is some notion of like a computationally bounded but sort of Bayesian player to the game. But as soon as you don't take into account things like the deviations and triangles, you exactly would probably be able to construct some sort of fooling polynomial for the natural moments.
So if I really want to fool SOS, I want to cook up a graph which has a large clique, but where for all smaller sizes of motifs,
what a large clique?
Yeah.
The graph with small clique.
I want to fool you into thinking that there is one. Okay, great. I'm still getting the...
Yeah, it takes a little bit of digestion and stuff, and
Head reshaping.
Any other questions?
yeah.
So this is the SOS hierarchy is a standard hierarchy that does not depend on the problem. But sometimes you can design hierarchies that are really much stronger. like
Yes,
somewhere
absolutely.
like
Absolutely. So for example, I mean, there's a few works on that, but you know, a lot of times if there's a lot of symmetry in the problem, then you can really exploit the sort of sparsity in what you need as a dual certificate by actually exploiting the symmetry. So I think there's a lot of hope for actually exploiting things like, you know, representation theory to create different types of hierarchies for very specific problems, but
So morally, so this lower bound would also hold for something like that?
so I'm not sure. See, I think that depends on which problem. So if you create a problem with a huge amount of symmetries, then I would believe that there actually is a way to create a better hierarchy that's somehow more concise by exploiting the symmetries. I'm not sure about SOS because, you know, after all, for things like random CSPs, when you allow general random CSPs, when you allow general STPs, there is this Lee-Raghavendra-Stoyer result that shows that actually lower bounds for SOS on the size imply lower bounds in general. So there is a sense in which there you can't really, you know, hope to use these types of asymmetries that much. So I think it's very problem dependent.
All right. Let's thank the speaker.